Greetings. Welcome. So in part one we talked about some strange things. I got a little carried away. Of a capacitor and a bifilar coil. So now, without further ado, the conclusion to a capacitor and a bifilar coil.
Okay, greetings, welcome. And so I thought I should probably get out a part two to this. I got a little carried away on the last one. I can't believe how strange it is. And it's still very strange to me. Some things are starting to make a little more sense. It might help if you watch part one for this to make more sense, but parts of it I still am not certain on as well even now. And there are some things that I found rather interesting. So just to try to rehash real quick, we got our two bus lines. We got a 0.01 UF cap. Those two white solid state relays break the positive and negative. So we charge this up, then we shut those off. You got your cap sitting here, and this one there then discharges the cap through the coil. The coil's a bifilar coil, and so it's discharging through one strand of the bifilar, and the other strand's not doing anything at the moment. So when you discharge this, and we charge the cap for 60 microseconds, just shut it off for 140. I also learned that you don't want to go lower than 140 with these caps, or you start getting weird things because they're just stepping on their toes, the switches. And then pin 9 is when we discharge the cap through the coil, and that's 300 microseconds right now, and then shut that off. And this is what we see on the oscilloscope, and it's drawing about 0.21 amps. If we just discharge this cap through a line, it would be something like 0.15, and we could actually calculate from the cycles per second and the capacitance and the voltage what it should be. But it's going to be a bit more than that because it's coming out of the oscillation there towards the bottom. So what is that, 0.21? So just real quick, if we change this to, I'm going to guess like 260, will put us closer to the top there. Yeah, so we change that to 260. We see that it looks like that, and we see we're drawing significantly less amperage. So this is all well and fun. Now, if we take, this is the positive of the cap. That's where the positive is going in. And that's this end of the coil. So if we take the other strand, which is here in the middle, and we connect it, we connect that strand out to here, and then we're going to take this yellow line and we're going to connect it to here, and that goes to there, which is the ground for the power supply. And when we do that, we start seeing stuff like this. And in the last video we kind of went over that you can change the timing and change this magnitude of oscillation. The Q factor stays about the same, but the magnitude of the oscillation now varies a lot depending on these parameters. And another thing that happens is we went from 0.07 to 0.48. So first thing, just to try to get my thinking on that out of the way, and also let's just connect the other end of the secondary now to the other end of this cap. And when I do that, now we got that. So you see things change a lot once you have that earth ground in there. Why did the amperage go up so much? And one of the things I said before is, like, it's sort of like being goofy, but the Heisenberg uncertainty principle. You know, when you go to measure, you have to remember when you're measuring with an oscilloscope, the oscilloscope is grounded. So here I've hooked the other channel of the oscilloscope up, and both of these are 0.01 UF caps. They're the same size, so they like to ring at the same frequency as well. And so we see both of the caps are ringing away there. But when we've hooked the oscilloscope up there, we see we have a ground here, we have a ground there. We also got the ground here. I mean, if I just remove this now, there's no change. because it's got the earth ground doing this. The earth ground from the oscilloscope doing the same thing as the earth ground from the power supply. I'm going to put that in though, just to. So here's where I made a little bit of progress on this. Is what if we remove the ground here from the oscilloscope? I'm removing that now. That's what we see. So what we actually have, I'm going to, since I'm going to leave this disconnected, I'm going to shut off channel 1 for a moment. And so if we just connect a line from this ground to where the negative probe of our oscilloscope was, that's kind of bent, but it's good enough. You see, it goes back to being all funky. So now we'll take that out and put it back in. So that was where I started to make some progress on this, because how's it described? Capacitors block the flow of DC current. They allow the passage of alternating current. There's your 0 points. So we saw them both flipping around positive to negative. So now you have a connection between your positive to a negative, the earth ground, through a capacitor that lets oscillating current pass. So that explains that. And I've been thinking about a number of ways to try to approach it. So a complicated way would be to only make this earth ground connection during certain segments of this and see if you can get some of that increased amplitude that we saw before without getting massively increased amp draw. Now another way, if I could switch fast enough, is you would shut this thing off before it's in a position to be shunting current out to earth ground, but I can't switch fast enough right now. That's what the cool kids do. They can switch down to like microseconds. I can't do that and stay opto-isolated, so I'm not going to worry about that. There's a couple of real simple ones that I haven't tried. One is, what if I just put in a resistor between this ground and this ground? So I'm going to try that, and I'll get back to you and see what that does. And the other, it's kind of like learning electronics as I go along. But I've heard about a choke, inductive choke, and just as capacitors block the flow of DC and allow the flow of AC, inductors block the flow of AC and allow the flow of DC. I mean, they don't always block entirely the flow of AC, but the reactive resistance puts a big resistance there. So I haven't done this yet. I'm going to do it, and then I'll get back to you and tell you what I saw. So I just put a 470 ohm in there. Well, let me show you the whole thing here. So here's just a direct connection. Looks like that. Here's no connection. Looks like that. And that went from point. What did it go from? 0.54 down to 0.12, and then connect it through the resistor. And it's not as good, and this has gone down a little bit, so that's sort of what I expected. I'm going to try an inductor. Okay, well, that wasn't what I expected. I'm like the sorcerer's apprentice, from the medieval tale. I have no idea what I'm doing, just throwing stuff around. So I just threw in a random coil of wire that I had lying around, and I thought it would be blocking things. Instead, this got larger and the amp draw went up, but we got quite the oscillations going on there now. So I think part of it is going to be going back to the idea of making and breaking the earth ground connection with the switch on the Arduino at a time that's beneficial. But that'll be a little bit complicated, and I don't want to go into it right now, as there are some other things that I'd like to show you with this as well. And you recall in the last video also, there's different behavior if this line is going to the positive and the other line is going to the negative than how it's set up here. If you reverse those two lines, the behavior is entirely different. But let's stick with this right now. And you see, this is what we were seeing. And let's zoom in a little, and I'll show you what really caught my attention. It's this part. This is where this cap is oscillating in voltage while you're charging the cap before you've done anything. And let's change the timing a little bit. So here's a pretty good example. So see, this oscillation is different than that oscillation. And what it looks like is that cap, we'll call that the purple cap, it looks like the voltage is being driven up when the cap just charges, which I found pretty astonishing. I've seen better examples of this. Is probably good enough. This is like a different oscillation. This thing got boom thrown up by the cap being charged, and that fits with Faraday's law of induction. It's just you normally think about it when something's discharging, but here it's charging. The other interesting thing is that at that point this isn't connected to there, so it's just the cap charging up and this one end of the wire sitting out there. So I was thinking, well, maybe you get rid of this. Now, of course, you still need to be able to discharge the cap. But what happens if we pull this line out and just put a short across the cap there? So what we have now is just this cap discharges, and then when that switch there goes, it charges up and then it discharges right across this white line just as a short. And you just have this guy hanging out there on the end connected to the positive, and the two lines hooked up there of the other secondary. And that's what we see. It's not all that much different than before. But this has no return path to ground, to any ground. It's just sitting out there. So all this thing cares about is seeing the change in the force there, the change in the magnetic and electric fields. And it's sort of an antenna, I guess you might call it. But it's not like, you only get 200 millivolts. It's kind of unchanged. Which is, there may be some corollaries as well that you might consider from that. We're still at the 0.58 there. But then I was thinking, well, we got rid of one line here, working fine. It just needed the grounds hooked up. Can we get rid of one of these lines? So if we pull this one out, this is the one going to ground, then what we get is that. Interesting, but not good. But if we pull this line out and we connect this line to here, when we do that, now we see something. Let's pause that. Now we see something that looks like that. And so that's still the secondary. I mean, I still have both ends of the oscilloscope hooked up. That's still the secondary going up to 10 and then ringing. It's a little different waveform going on now, but it's still going out there. And we just have this cap discharging, and then there's one wire hooked up here, and then there's one wire hooked up here. And this has gone from 0.58 down to 0.23. And I believe that's because there's no longer a direct connection to the ground. It's connected to ground through the cap. But it still works fine. We got rid of a lot of that excess amp draw. And it's also amazing to me that this is hooked up across the cap, and the cap is still oscillating. It discharges through the short, but then the short, that's not hooked up all the time. So when it's not seeing that, but it's seeing this one line there, then it kind of gets in on the action and oscillates for a little bit too. And we could extend that out and look at it more. But I'm just saying, it's hard to get rid of these oscillations. Again, it goes back to the Sorcerer's Apprentice, where he keeps breaking the broomstick, and then he's got 5 broomsticks all sweeping. It's like, how do you can't get rid of it. I mean, you just keep taking wires out and it's still oscillating. So seeing as that cap is really just to try to get a sharp pulse, do you need that? You can probably get rid of that. And then the last one that we'll look at and then wrap the video up is if you're pulsing this cap along this line and this guy's just going to have one leg there, and the other leg is going to be out in space. What if you made this a coil? What is that going to do with that? Might as well, you pulse this through a coil, then you can draw it off in a manner analogous to a buck boost or something like that if you wanted, and see what happens with that. So let's do the first one of getting rid of the cap. Now I can't just leave it as a short because it'll probably blow up the switches, but we can put in a small resistor, maybe like 20 ohms, and see what we get. Okay, I've left everything the same and just put in a 20 ohm resistor. So now this thing isn't doing anything. It's just to it's basically just giving these a break because this has gone through the roof up to 86 milliamps. And at first it doesn't look like much, huh? But we've forgotten something, haven't we? We always had another ground hooked up there, so I could put a line in, or I'm not even going to hook the other part up. Just going to put this ground so that we have ground there and there. Now that's what we see. And we can even look at the oscillation. I mean, there's our square wave. I mean, there's no oscillation, a tiny bit. I don't know, that's just the resistor that it's across. So it's hard to get rid of these oscillations. Now the interesting thing that happens here is, let's see if this works, because sometimes there's like other oscillations. I don't know if it's like oscillating with ground or what it's doing, but sometimes it doesn't go as I expect. But let's see if this works. So we've got pin 13I, 60, that's where it's just going through the resistor, and then that shuts off, and then this doesn't do anything, this doesn't do anything, but it lets the SSRs rest for a minute. But we can, I mean, they're not, it's only 89 milliamps, I think they're half amp relays, so we can go up to, let's say 80, and let's see if it does what it was doing before. Yeah, now nothing else changed there, but this is up to 99.8. So there are like different oscillations going on here that I don't fully understand, but the general trend will go to 70, and the amp draw went up. 70, and amp draw is going down, and then we'll go to 60. Yeah, that's where we were before. Let's go to 50. I think there's going to be this oscillation that I don't understand coming into play, but if not... Okay, so the amp draw is still going down. And let's go to 40. 40. Sorry, bear with me. Yeah. It looks kind of familiar, doesn't it? It looks like the way in the first video, the way the oscillations would change. I don't know how low we can get. I'm going to try 35 and 30, and I bet it's going to start going the other way. And all this time the amp draw is going down. Yeah, it's just starting back up, but we won't be able to go fast enough for it to really take off. Yeah, 35. We're at 30. Can we get to 25? Yeah, we can even get to 25. If I go any faster, it's just not going to turn on. But you can see it's starting to get the larger oscillations, and all this time we've trended downward from close to 100 milliamps down to 50 milliamps. And this oscillation is happening essentially independent of that. And that's because if this was connected to the other end, you would say that it's the peak amp turns that determine what you're going to get in terms of a displacement spike. You know, with with Faraday's law of induction. It doesn't care if you're at a particular magnetic field strength for a million seconds or a nanosecond. It's the change. That's what's kind of strange about it. It's the change in the magnetic field that generates this. So, in other words, now, I haven't been able to get anything useful, of course, out of this so far, but the general trend here is that you can go faster and faster with the pulse, and your amp draw is going down, but it's not causing this to become smaller. So if you could switch really quickly, and or you had a really big coil, then that's another approach to this. Let's look at one last thing and wrap this up. So this is kind of silly, but I just took this 10-pound coil and hooked it up so that we discharged this across the 10-pound coil. And I did that because there's going to be a tremendous mismatch in induction between here and here. This is like 70 or 80 and this is like 12, so they're nowhere near matched, and this is fairly high Q. So the first thing we see is it looks like that, which is not pretty, but it's not bad. That's like a little over 6 volts there. This has gone way down. I don't know exactly why. I'm sure it's had enough chance to discharge with 220 microseconds, but we're only got one wire on the secondary, so let's try and hook that up as 2 wires. Okay, that way didn't work, and the amp draw is way high, even though you wouldn't expect it to be. Let's switch those around. Well, it looks kind of like what we had before, except for now instead of drawing 0.06, we're drawing 0.55. So, 1 wire on both that and the secondary is the way to go. And even with a mismatched thing here, I mean, of course, the next thing to do is either with the cap or just, well, hell, let's do that too. All right, very last thing, let's just get rid of the cap once more. Instead of using a resistor, we'll use the inductor. All right, well, that one's kind of interesting. We're up to 1 milliamp, but it's better than 90. And this is all off the scale, so let's see. Wrong way. 10, 10. The purple is doing that up to a maximum of 33 volts. And what's the... Okay, the scales aren't matched. The Vmax of that, well, there's no cap there, so the Vmax just of the coil there is 98 volts, or 70 volts and 96 volts minimum. So the last thing there would be, put in a backwards diode and pull that off. Would be kind of fun. Anyways, as I'm saying, it's, I feel like the Sorcerer's Apprentice, but you see a lot of cool stuff. That's it. So, I find it interesting. I don't know if other people do, but thanks for coming along. Stay well, and I will talk at you more later. Bye-bye.